Hello, you're back live. All right, back for another hour and a half ish, a little more. Here's the plan. I'm going to go through the rest of the article. I'm going to proof the rest of this, maybe grab images for it, pretty much have them ready. And then I'm going to spend, hopefully I have an hour left after that to edit the camera ready. I really don't care all that much about the pub. I guess some people read it. I guess. So I'll like make sure it's updated as best as possible, but it's a whole generation outdated, so yeah. Let's just go through this out loud. We'll proof this. If anybody has any suggestions, let me know. And we will go from there. So I already read through this section. So 1, build a simple environment and train an agent. Read the introduction to my RL Quick Start Guide. Just the first paragraph for now. You now know some... You now know some words we use in RL and not much else. Read the Pufferlib docs on writing your own environment, including all the link code on the squared sample environment. So I have to still update these docs a little bit. Map the terms from the introduction to this code. Observations, actions, rewards, and terminals are just arrays. The observations are input to the agent's neural network, which outputs actions. Rewards determine whether the agent has reached its goal, at which point the terminal value is set to true. You don't yet know how we use all these things to actually train. You don't know how we use all these things to actually train yet, and that is fine. Also, let me delete this bot message out of there. Oops. All right. Write your own puffer environment. Keep it so simple. And we're just going to say write your own environment. So write your own environment. Keep it so simple as to not even be useful. That will come next. If you can't think of anything, do a stripped down version of Flappy Bird on a 2-block tall grid. The agent can move either up or down and observes whether there is a wall on the roof or ceiling above. That didn't make any sense. Whether there's a wall on the roof or floor. -1 for hitting the ceiling, 0 otherwise. Bind it to Pufferlib following the docs and train your first agent. Ask in Discord if you get stuck. Let's link this to copy. Two, learn the most basic fundamentals. Read Karpathy's policy gradient blog, including the implementation. There are a few very minor details that are dated, but it is otherwise still the best introduction to on-policy methods. You should now understand how policy gradients turn observations, actions, rewards into derivatives over weights. You have also seen discounted reward as your first example of an advantage function. Understand that the discount factor mathematically determines how much you care about reward now versus reward later. Read the fundamentals section of my RL Quick Start Guide. I'll give you context for the basic classes of methods. Don't go down a rabbit hole of reading papers just yet. All modern algorithms are at least slightly off policy, and the strict definition does not matter as much anymore. Read the multi-agent bullet point twice. Read and train Puffer Target. This environment is included in the same tutorial you already followed. It is multi-agent and significantly more complex than squared. The agents no longer move on the grid and have to solve a more temporally extended problem. Every agent sees a normalized distance measure from itself to every other agent and goal. Agents only receive a sparse reward of 1 for reaching their goal. Follow the docs To train an agent on this environment, it should only take a few seconds. 3. Build a slightly more complex environment. Make something about as complex as Target, max 300 lines. Doesn't have to be multi-agent. If you did grid-based Flappy Bird before, do the full game. Any similarly scoped project should suffice. Think about what data the agent needs to see in order to play, and make sure that it is included in the observations. Reread the debugging section of the Quick Start Guide to avoid common errors, and post on our Discord if you get stuck. Is there a debugging section in my Quick Start Guide, or am I misremembering? No, there isn't. It's the tutorial. Reread the quick start of the Reread the debugging section of the custom environment doc to avoid common errors, and post in our Discord if you get stuck. Aim to train an agent that you can visually confirm is playing the game well. Read other puffer environments. Snake and Convert are two slightly more complex, I'll put this caps, are two slightly more complex environments with clean code. I'm going to do simple. Clean code has the annoying, like, because of the stupid book, but it's just clean code. It's not clean code from that stupid book, but it's clean code. Multi-dash agent. So, I never know what to do with that, man. Because if you don't make it one word, if you do multi-dash agent, then you need to do single-dash agent for symmetry. So I usually just make it one word. Like if we just, isn't this a thing? Does everybody dash it and am I just stupid? No, it's that it's auto-correcting. I guess most people do dash it. Annoying thing. It looks super stupid to me written this way, but whatever. You can also start looking at some of the arcade games like Pong and Breakout. By now, you've probably hit a few bugs and can start to appreciate the ways in which things can go wrong. We mitigate that by keeping code simple and minimally abstracted. The biggest mistake you can make in RL is to underestimate the price of complexity. Enhance your environment. Add some features that make the problem a little more interesting. Retrain with different versions and see how your changes alter the agent's learning. Aim for something on the level of Pong or Snake. If you get something visually interesting and not already in Pufferlib, come show us and PR it. Many simple environments end up being quite useful in research. 4. Start understanding why that worked. Read the core algorithm paper. It is dense, but the actual algorithm is simple. Read the bullet point on PPO from my quick start guide first for some intuition. Then you can read the proximal policy optimization PPO paper. You can ignore the TRPO and KL penalty sections. The main equation 7 is just saying clip the policy gradient and weight it by the advantage function, then average over a batch of data. The advantage function is generalized advantage estimation. If you have a strong enough math background, read this now. Otherwise, put it off until section 6. section 6. Understand why I didn't have you implement the algorithm. The common reference algorithms are extremely fiddly. Read cost us 37 implementation details of PPO and the associated CleanRL PPO implementation. Not particularly long, but the details really matter. Read our other articles. They are simpler than academic papers and tell you exactly how the tools you have been using work. Stronger hyperparameters with protein, buffing up PPO, Neuralumma Mo30. Cool. 5. Your first real project. Finish reading my quick start guide. You will not have context for all of it just yet, but it contains a lot of useful perspective as you start to solve harder problems. For example, depending on how hard your environment is, you may actually have to run a hyperparameter sweep to get a good policy. Now this is fine. It's repetitive, but it's fine. If you have a short horizon environment, you may need to at least decrease the discount rate. Do you understand why? Let's actually do a little less. Connect 4 maybe. Yeah, if you implemented something like a card game, you may need to at least need to decrease the discount rate. Do you understand why? Cool. Read the Pokemon RL blog post. This is a powered by Puffer, trademark, copyright, registered. I will leave it like this. Project that beats the entire game using pure from scratch reinforcement learning. The observation space formulation, reward engineering, and problem setup are all informative. Note that Pokemon Red is 1,000 times slower than most of our RL environments. You will almost never actually have to do this level of engineering when you have faster simulators. Pick an interesting problem. Aim for something you can do in 500 to 1,000 lines, depending on your programming background. Several useful environments have been shorter than that. Arcade games are usually a good choice. Just check in the Discord that nobody is already doing the same one. If you have experience in another field, applied problems are even better. Good RL environments look like fiddly interactive optimization problems that are quick to simulate and have clearly defined observations and actions. The initial drone environment was only a few hundred lines. Solve and PR to Pufferlib. It may seem self-serving, but this is genuinely the best way to learn. We have an active community of researchers and hobbyists large enough that someone will nearly always be around to answer your questions. Many environments that you wouldn't expect to be useful actually help us advance core RL research. 6. Do your homework. The list of important papers to read in reinforcement learning is quite short. See my programming and ML advice article and my quick start guide for perspective on why this is the case. I need to link these, right? Let's do that real quick. Oh, actually, we can link the X version. Copy the link. And then we can't link the ML article until it's published. So that'll be the final tweak. These are the top 10 papers you should read regardless of what you want to do next. This list is intentionally not a historical account of mostly broken algorithms. My focus is on the major capabilities defining results and the commonalities among them. Note that almost all of the OpenAI and DeepMind results have associated blog posts that are more accessible than the formal manuscripts. You can start here, but you should also read the full papers if you want to do research. We have a couple papers on Pufferlib and NeuralMMO that you can read if you want. You're better off just reading our blog docs and the source code. Dota 2 with large-scale deep reinforcement learning. My pick for the most important paper in the field. PPO with a single layer LSTM solves Dota. One of the biggest errors you can make is to undervalue this result. Go play the game if you need convincing that this problem is meaningfully hard. Do not skip the appendix. Grandmaster level in StarCraft 2 using multi-agent reinforcement learning. Actually, I've seen many top researchers undervalue this result and waste their time developing fancy methods that solve trivial problems. This is true. Go play the game if you need convincing that this problem is meaningfully hard. Do not skip the appendix. Grandmaster level in StarCraft 2 using multi-agent reinforcement learning. Another extremely hard problem solved with RL. It's number 2 because DeepMind bootstrapped with imitation learning and use significantly more complicated methods. They tend to do this often, and I am not convinced it is required. Mastering the game of Go with deep neural networks and tree search. This is a landmark historical result that kickstarted the field. You could arguably place it higher, reasoning about comparative complexity of Go is hard. The naive branching factor argument breaks when you look at games like Dota or SC2. Learning dexterous in-hand manipulation. Learning to manipulate a Rubik's Cube with reinforcement learning. With a robot hand. Reinforcement learning. Kind of jumped the gun there. This project pioneered domain randomization, training on a ton of slightly different problems to improve generalization and robustness. Open-ended learning leads to generally capable agents, also known as XLAND. Heavy domain randomization allows agents to generalize to new tasks not seen during training. You could do this as randomization over training tasks allows agents to generalize new tasks not seen during training. There are a bunch of conflating variables here with method changes, but the end result is a pretty compelling argument that RL can generalize. Emergent tool used for multi-agent autocurricula, 3v3 hide and seek with movable objects. A pure version of techniques used in Dota applied to a simpler but still complex task. Human-level performance in first-person multiplayer games with population-based deep reinforcement learning. 3v3 capture the flag with FPS mechanics based on the associated Quake game mode. The NetHack learning environment, a really hard environment for reinforcement learning. Probably can't solve it with a general method without also solving AI in the process. We call that AI complete. I call that AI complete. I don't know if anybody else uses that. Proximal policy optimization, the core algorithm that is the basis of most modern RL. Built our Pufferlib 3.0 algorithm as a set of enhancements to PPO. High-dimensional continuous control using generalized advantage estimation. Advantage function that is half the reason PPO works. One of our 3.0 experiments was to combine GAE with vTrace, playing Atari with deep reinforcement learning, the original deep Q learning paper that spawned the field of modern RL. Cool. This is the new section I wrote this morning. We'll see if I actually like it a couple hours later here. My best advice in one place. How to approach a new problem. Start from first principles. The agent is learning tabula rasa. It's a blank slate. At the start of training, it's looking for signal by mashing buttons. It also can't see. Imagine the environment has the graphics completely randomized. Some reward has to be obtainable this way. To actually learn from this reward, the agent needs to be able to see. What information does the agent need to solve the problem? Make that the observation space. Ditto for actions. What information would tell you if your agent is working correctly? Log that. Almost always want a single real number metric of overall performance. Don't only log raw reward because you will probably tune the scale of this number and make results incomparable. Log a score instead. For example, we might give agent a reward of 0.25 or 0.5 for breaking a brick, but we log the actual number of points obtained. Bonus points if you can scale it to the range of 0 to 1. Log any extra data you will actually look at, but don't log a ton of stuff you won't use. Good candidates include collision rates, out of bounds, etc., since these are sanities that should drop to near zero for applicable problems. Right, the simplest possible environment that is still fast. Don't abstract anything. That's important enough to say twice. Don't abstract anything. Start training early and frequently. Want iteration speed to be as fast as possible. You muy bien, directo. Hey, welcome, Alan. Bienvenido. That's important enough to say twice. Don't abstract anything. Start training early and frequently. Want iteration speed to be as fast as possible. Seconds is better than minutes. You've lost if it is hours. If training does not work, suspect your data. Make your environment playable. Is what is happening sensible? What you see happening sensible? Do you see reward being assigned when you expect it to be? Run an evaluation on a checkpoint. See if agents have found some degenerate, unrecoverable state. For harder problems, scale up slowly and don't make a ton of changes without training a decent model on the latest version. Don't experiment with new algorithms on new environments that are constantly changing. Do your research on stable problems, then try it on the new environment. How to encode data. Normalize the observations appropriately. You want position data to be egocentric when possible. You can do this by subtracting the agent's position, dividing by the maximum value. Street data can't just go into the model without encoding. If you represent knight, king, queen, pawn, rook as 0, 1, 2, 3, 4, putting that into a model raw implies knight is more similar to king than it is to rook. It also forces the model to learn a wonky decision boundary in latent space. One hot encode knight as 10000 instead. You can do this in the environment for very small values, but do it in the policy for larger values to save bandwidth. Actions should be the simplest possible set of controls for your environment. I like to imagine the environment being released for Game Boy and designing the controls to match. Neural MMO 3 features exploration, combat, equipment, consumables, progression, and a live market. The action space is a single discrete, and the game is playable with keyboard only. Don't blow up the size of the space to accomplish this. Okay, so this is super dense, right? But even though this is ridiculously dense, this is pretty much like, this is like a non-negligible fraction of all the intuition you need for reinforcement learning in a page and a half. So I think that that's worth it. I think it's worth doing something like this. I haven't written anything like this before, so we'll see what people think about it. But this is kind of my best advice in one spot. Is doing what you're supposed to do. Roll it. Hey, welcome, Shadow. Is there anything in here that is straight up confusing or doesn't make sense to any of you watching? Please tell me now so that I can make edits or clarify things or what have you. Also, welcome YouTube folks. Ah, cool. quite a few people today. It's funny that we have the same number of people watching me literally write an article as we do actually doing RL code. But yeah, welcome. This is the beginner's guide. I guess it's beginners all the way up to state of the art, so it's not just like the basics. I'm doing this mostly out of request. People have requested this repeatedly. There's also a companion article that starts with programming in ML for like really basic stuff. The full journey. Yeah. I mean, because basically the thing is like the way that I got into research was pretty self-directed and it was like very meandering and independent. I kind of just tried stuff, read a bunch of papers, tried other things, started doing research, which is literally doing research is just like read a paper, like read a couple of papers, get some ideas on how they could improve, try to improve them. If it actually does improve, like write something about it, try to publish it, do that in a loop until you get better at it and you get better ideas. So this will be what you can point to when new folks come in. Yes, this is going to be like the overarching, like this points to all my other articles and has a basically step-by-step guide on this is how you learn reinforcement learning. Do this, read this, do that, do this, read this, do that. Like now you know RL. Will you publish it today? No, I think what I'm going to do with this, because I have to, well, I'll finish editing it. I got to get images for it. And then probably I'll make a post that this will go live at 10K followers. Because I think that would just be a fun thing to do. And we're basically, like, we're almost at 10K anyways. So I think that's what we'll do. 10K on X, not YouTube, obviously. All right, let's finish reading through this. And if anybody has ideas or questions or things on any of this, please speak now so that I can make the edits before it's live. Advanced topic, applications. You have deep knowledge of another field. Use it to look for problems where RL can help. These tend to have the same feel. Let's not split my infinitives. These all tend to have English. These all tend to have the same feel. RL works when you have a fiddly, interactive optimization process and build a fast sim. To give you some ideas, we're currently doing open source work on drones and logistics. Both are areas where we can easily build simulators that run millions of steps per second and a few hundred lines of basic C. Multi-agent, multitasks stuff are going to be a lot better with images. You are correct that I did not include any images in this at all. The funny thing with multi-agent and multitask, Shadow, is it doesn't change the architecture at all. Like, it literally doesn't change the architecture one bit. Is that news? Like, is that surprising to you? I have a bullet point on this, but it's like, yeah, people make multi-agent out to be way harder than it is. My PhD is on multi-agent, and it's literally the same thing as single agent. Separate encoding idea. A little confused. I'm trying to solve a Rubik's Cube with RL since I met you on Twitter. It's been a fun way to go. Ah, cool. Yeah, we had a couple people like mess with that, and nobody ever actually finished that project. So, yeah, if you want to do that and as an end, we'd very happily take a Rubik's Cube environment PR. It's probably like, you can probably write a fun 3D renderer for it very easily as well. Like, you could probably even make one with like the rotation animations, and it would probably be maybe 200 lines of Raylib code. Without the animations, it would literally be like 20 or 30 lines of Raylib code, probably. Maybe 50. The separate encodings idea is a little confusing. Separate encodings idea? Do you mean, is it actually, I want to understand this. So, Shadow, is it specifically something about this that's confusing? Because nothing that I wrote here has anything to do with multi-agent. Or are you talking about, like, entity encodings? So here's the funny thing with entity encodings. Lately, I've literally just been like putting them into the observations flat without an entity encoder and just maybe sorting them by distance. And this kind of works just as well. The problem with entity encoders, in order to do entity encoders fast, you need custom CUDA. And we have not actually gone through the effort of doing that because it's the type of thing that would probably take me several days. Mostly because of the annoying bindings. Imagine you have image and vector obs. Yeah, so you'd have like a vector per agent, right? Yeah, I know what you mean by entity encodings with that stuff. It's like point-wise, kind of, or entity-wise. You'll get that from the papers, to be fair, that I've suggested. And it's a niche thing. But, like, I don't know if I even want to recommend it generally, because the thing is, like, it's actually very slow if you do it naively. Like, it's really slow. Probably the biggest problem we have in the driving sim right now, right? The biggest problem we have in the driving sim is that there's this really slow point-wise encoder. And without custom CUDA, it's just there's no way to make it fast. Let me keep reading through this. Longer term, we are most interested in applying RL to hard science and manufacturing. Are there areas of molecular simulation where we can cut corners on fidelity? Are there constrained areas of robotics where the current simulators are massive overkill? What about in the production of goods? There are likely problems where nobody has even thought of building a sim. As a quick plug, if you want to join us on the business side, this is the best way. If you can build a prototype and we can find a client, we'll build you a board for the contract. Build a prototype and we can find a client, we'll bring you a board for the contract. Here are a few successful applications, and I link the Nuclear fusion, driving with lift, commercial cooling systems, self-driving, and fusion. Cool. Advanced topic, algorithms. You need a good enough math background to be able to understand publications in this area, and a good enough programming background to run your own experiments. Expect to read a larger number of papers critically. Most published results are more published results are wrong in RL than in any other than in other areas of AI. Ugh. Even the ones with strong evidence. Here are a variety of research areas with important open questions and some of the relevant papers. Off-policy learning. During the peak 2019 golden era of RL, OpenAI mostly used on-policy methods, while DeepMind used off-policy ones. DOTA and emergent tool use are clear-cut confirmations of on-policy methods working in relatively clean settings. We don't have the same thing for off-policy methods because the main DeepMind results tend to have more moving parts. On-policy methods work great and fast with unlimited data. On-policy methods work great and on-policy methods work great and are fast with unlimited data. Off-policy methods are sometimes favored in data-poor settings. Can we get the best of both? Here are some papers we're looking at. We've got Rainbow, the first usable off-policy method to compute DO. It's a kitchen sink disaster of tricks bolted onto DQN. That's not an exaggeration. Beyond the Rainbow, this paper hasn't gotten any attention yet, but it is a good follow-up to Rainbow that balances sample efficiency for relatively slow sims with decent wall clock training time. I rather like this paper. Human level Atari 200 times faster. It's only 200 times faster if you count environment steps and treat compute as free. only 200 if you're counting environment steps and treat you're counting environment steps and treating compute as free. The result still holds though, so there's probably something here. Hala introduces vtrace to correct off-policy drift. We tried this in Pufferlib 3.0. It was worse. It was just worse than JE. It did help a little overall when combined with JE, but not specifically for off-policy drift. Model-based learning. Can you compress transitions? This is not true, actually. We'll just say it like this. Model-based learning. Can you compress transitions by predicting the next state? Good enough math background. Is that undergrad, grad level, just thinking the phase and rigorous, or you're saying go check the papers and see math? Where do I say good enough math? You need a good enough math background. So that is from my other guide. So the criteria I give you here for having a good enough background, it's from the intro. You can see what you think of this. Basic deep learning knowledge at the level of Stanford CS231N. So if you've gone through 231N and you understand that, then you're probably good enough with the math. And then on the programming side, it's can you implement an LSTM without importing anything? Also, if the implementation you thought of was over 100 lines, probably should look at the programming article. I'll put a little parenthetical in here. You need a good enough math background, 231N, to be able to understand publications in this area, and a good enough programming background to run your own experiments. Expect to read a larger number of papers critically. More published results are wrong in RL than in other areas of AI, even the ones with strong evidence. All right, cool. I'd already read all this stuff. Model-based learning. Can you compress transitions by predicting the next state? Various methods attempt to do this and then learn within hallucinated data generated by the model. Others attempt to just use the model as an auxiliary loss. Science in this area is iffy, and I don't trust the reasoning behind any of the published results. There is very likely something here, though, possibly as an alternative to off-policy resampling. Recurrent world models facilitate policy evolution, original world models paper. Mastering yada yada. This is probably the best known paper in the space, Dreamer v3. This somehow scales to 200 mil parameters, which usually doesn't work in RL. And then our paper, showing that the tricks introduced in Dreamer v3 don't work according to the reasoning given. Yeah, this was one of the papers that really burned me the most, actually, I would say. Because it's like really well-known paper, really well-known author, and the result is not wrong as far as I can tell. And like people have done stuff with Dreamer, but the code is a disaster, and none of the reasoning given in the paper actually holds up to ablations. Like at all. Search. Can you explore or simulate chains of different possible outcomes, improve learning and or test time performance by leveraging more compute? Worked in several DeepMind projects with and without access to simulator dynamics, but has not really been used more broadly. Mastering Atari. I don't think, yeah, I'm pretty sure it's not really been used more broadly. It's mostly DeepMind doing this style of stuff. Mastering Atari, Go, chess, and shogi by planning with a learned model. Mu0 removes the requirement from AlphaGo that you need to be able to set the simulator state. Go Explore uses settable sim to gimmick very hard exploration problems unreasonably well. To be fair, if settable state is useful, we can build it into almost every type of sim. Efficient 0, built on Mu0, claims to beat Dreamer v3. Advanced topics, infrastructure. I'm writing this in the context of Pufferlib's infrastructure since we unambiguously lead here. That is a true statement. There is just no other good infrastructure. Our models train at 3 to 5 million steps per second in PyTorch eager mode. Napkin math says that we should be able to double this performance on our larger models and 10x it on smaller models. Everything has to get faster to keep up. Environment speed. Read our envbinding.h file. It is responsible for defining those magic vec reset and vec step methods. Except that there is no magic, we're just creating n copies of your environment and running them in a loop. The magic logging method is just iterating through fields of your log struct and dividing by log n. We have this set up for you because Python to C data transfer is tedious and error prone, and the boilerplate is roughly the same for every environment. It is set up so that it is fairly easy to get access to individual environments from Python if you need it as well. We would like to build in settable simulation state, but we have not thought about it too much. The point is, this is pretty much the lowest overhead thing we can do. Data does not have to be copied between C and Python during step. Both have access to the same data pointers. Next step in optimization here would be figuring out general approaches to improve caching and SIMD. Parallelization. We have a Python implementation of envpool. I don't really need to say that. Python implementation of envpool as of 3.0, round robin n-way buffered by default. All buffers are allocated in shared memory. Each environment is given a pointer to a block of memory. The C process writes directly to this memory, making the entire batch available to the main thread immediately without extra copies. So already almost as fast as it possibly could be. It may be possible to buffer the actual CPU to GPU data transfer because this is a big chunk of overhead on fast environments with large observations. Models and training. This is where the biggest opportunity is. Very few common operations like entity embedding where we don't have custom kernels. Stuff needs to be more fused in general, and we haven't gotten much out of compile, torch compile, or low precision. To be fair, we haven't even tried to tune BF16 on A100s or H100s, and BF16 is nerfed on consumer cards. We should be computing model flops utilization and seeing how close we are getting to the limits of the card, but we aren't. Right now, Pufferlib's performance depends strongly on using thousands of parallel environments, large mini batch sizes. I'd like to have less performance degradation with fewer environments and smaller mini batches. Bonus, work with Puffer. I said this would be an opinionated guide. Puffer AI is a comprehensive effort to fix everything wrong with reinforcement learning. If I thought there was a better approach overall, I would be doing that instead. Pufferlib is free. A free and open source project, and at this point, most of the code is written by contributors. We absolutely need more help on the core. It's only a few thousand lines, but this is where the most experience is required. This is where we are making the key enabling breakthroughs. And working on this is the best way to understand and contributing is the best way to understand the cutting edge of reinforcement learning. We're in discord.gg/puffer to get involved. If you found this guide useful, please take a moment to start Pufferlib on GitHub to support our work for free. Cool. That is a nearly 4,000 word guide. So yeah, this is basically 25 pages worth of articles. We used AlphaZero to solve an industrial problem. Oh, cool. So you must have had settable sim state then. Can I ask what organization you're with? That's cool. Previous company, but here's the article. Oh, it's not gonna let you link it. If you just give me the name or put it in the Discord, either way. I don't know. Twitch might like auto time you out for 30 seconds for links or something. I don't have anything enabled to do that, but basically none of the major streaming sites like it when you link stuff because of all the spam bots. Text to Discord, sure, I will look at that. Hey, hey, hey. I'm happy with this. I need to generate images, but I will. I'll make a tweet like tomorrow or whatever that this goes live at 10K. For folks watching, I have this article here, yes, and then I have this article here. 2K words, 4K words. This is the main content I plan to put out for education, at least the next chunk of time. I don't want to be spending too much of my time on just educational content. I will update the docs page on custom environments to at least include a little bit more about our API and how that works, because clearly people don't fully understand that. Is there anything else in here or any general questions? Let's just put it out this way instead, because like you haven't read the whole article and probably people have not been here listening to me yak for the whole time. Do you have any general questions, anybody here, about reinforcement learning or how to do things or how to learn things or how to approach things? If so, type them and I will see if I think that they are answered by any point in this article. If not, I will make a couple quick revisions. Education content creates a feeder into the community. That is the general idea, right? So we have this project, it's open source. I only have so many hours in the day, and I only have so many hours like that I can work consecutively for like a month straight before my brain just needs like a break. So ideally, if we have more people that are like actually competently going about this stuff, especially in the areas where I do not have the time, it would help a lot. There are areas of research at the moment where it would be great to get help. It's a lot harder to get into that stuff, but I think that a couple of our contributors are at that level now. They're just doing other stuff. So, like, it is very doable to get to this level, especially if you come in with at least, like, basic AI knowledge and a basic systems background. You can write decent, simple, low-level code, and you have AI knowledge at the level of CS231N. The rest of this stuff can be learned very quickly. Got the link via Discord. Oh, it's probably DM'd. Yeah. Oh, cool. Yeah, yeah, yeah. So this is actually, dude, this was the exact thing that this is literally the exact type of thing that I was thinking about with Puffer. I didn't know that anybody's done this yet. Like when I'm thinking of really valuable applications to for AI, like thank you actually for this article. I'm gonna send this to my contributors. Thank you very much for that. That's like one of the problems because we're looking for like really valuable problems where we can potentially do stuff. And that's like a huge market as well. Because basically, if we get one of these big ones, right? If we get like one really big job where we're able to just crush it, right? Then we're kind of funded for RL for the foreseeable future, and we can just keep doing cool science. The challenge env is still available. Cool. Oh yeah, we can. Yeah, this is sure we can crush this. Logistics, yeah, we can crush this 100%. We do have to be able to do our own sim, but because we have to have the sim be fast. But yeah, we can crush that. Have you seen any of the other stuff around Puffer Shadow, like our new algorithm stuff and like some of our results? To give you a quick idea here of like the type of stuff we've done. We do ludicrously high performance sim. Not really doing anything special, honestly, just by like not doing stuff the slow way that people normally do it. And we have our RL optimized end to end to be able to actually handle that amount of data. And we can just train stuff on just crazy, crazy amounts of sim. Like, you don't really have to do anything super smart on the algorithm side when you can do this. We do actually have our own algorithm research. So we use PPO kind of, but ours is a lot better than what you would expect normally. Different optimizer, trajectory filtering, different advantage function, a whole bunch of improvements. But yeah, cool. Never on sim, they rebuilt it. Yeah, if you yeah, Shadow, if you don't have documents preventing you from legally doing so, like message us in the Discord, because the thing from the article is true. Where like if you have domain knowledge in an area and you can help us get a contract, you can get a cut of it. If you help us like set it up and you want to work it. Because we are very well positioned at this point with all our sim stuff to really crush any sort of problem that looks like that. We are really well positioned to just crush. So there might be an opportunity there. What exactly reinforcement learning? What is the right context to think of it? Is it comp sci, math? What is the motivation for it? What keeps the space fruitful, progressing real world applications? I don't know if that's in the scope of what you're trying to do. Arguably, you're right that I haven't really sold like why learn reinforcement learning. This is fair. Not working for that company anymore. Oh yeah, no, I wouldn't ask you if you were. That would be, I'm sure that there would be legal problems there. That's why I'm asking you, right? Like our outreach stuff has been pretty dang successful. Um, at this point, like people are kind of starting to see what we're doing. Credentials help a little bit. I don't know what it is. Um, and like we've kind of been we've had a good time so far, like talking to people in tons of different industries. The hardest thing at the moment is kind of just finding those clear-cut reinforcement learning applications where we can make something super valuable and like carving them into RL problems. So if we can do that and get that to somebody, that's like that is super valuable. Yeah, so Jason, I gotta think about that a little bit. Like, do I actually want to try to I could just add like a thing here. It should be in the first paragraph. So I mean, I guess the way that I answer that, Jason, is it's an empirical science. It's a sub area of artificial intelligence, which artificial intelligence draws on computer science and discrete math for the most part. Uh, it is the branch of AI that deals with learning through interaction. So agents learn by interacting with an environment, the real world, a simulator, what have you. It models the way that we learn in a way kind of that other branches don't. They're trained supervised or on big corpuses, fixed data where you have no effect. You can't affect your data. It's been applied to a bunch of spaces, but what keeps it fruitful? Not. It's like not at all. It's stuck. There hasn't really been like the amount of progress has slowed to almost a halt since 2019-ish, and that's what I'm trying to fix. So, 90+% of the time, my content around here is focused on I am a scientist, I am doing research. How do we make reinforcement learning work at a core level, algorithmically? How do we get it on tons of different applications in the real world? How do we do that whole loop? This is the rare piece of educational content I'm doing because people have asked for it a ton. We have a ton of people on YouTube today, so hey, welcome everybody. Yeah, if you're new around here and you want to see some cool demos that just run in your browser, we've got Puffer Ocean here. So there's everything from like just simple arcade games, like more visually interesting kind of stuff. These are all neural networks playing in your browser as well. Got like this MOBA, it's kind of like a stripped down League of Legends or Dota type thing. We've got, what else we have in here? Oh yeah, we've got drones. It's not all games. We do like games though, because games are really easy to interpret. This is my, the follow-up to my PhD thesis, Neural MMO. Like 1,000 agents running around in this virtual world where they can fight and get armor and tools and equipment, and they can trade with each other, and they can level up in different things. Full game. Be the Johnny Appleseed of RL. I do want to make it accessible, right? The thing is, this almost kind of happened a little bit by accident, if you think about it. Because what I did here is I was focused on how do I advance the cutting edge, right? How do I advance reinforcement learning research? And in the process, right, the way to advance reinforcement learning research was to dramatically simplify and accelerate a lot of the existing stuff. So in the process of doing that, we made the entire reinforcement learning stack a fraction of the size that it used to be, and we made it so that people can actually do experiments on their laptop now in seconds, where it used to take hours in big, fancy, complicated machines. So that made it really accessible, and we started getting a lot of new people, where originally I had intended this to make it easier for RL PhDs. Now it's like brand new programmers. So it's come down a huge amount, become way more accessible. And that stuff is nice and useful, but it's not the main thing, right? It's kind of like a byproduct. The main thing on my plate is fixing the field, like advancing the science. That's the main goal. And I invite all of you to come join me on that because it's a very exciting area of science, and it's probably the last area of AI right now where you can make huge, huge advancements without needing a ton of capital. Welcome, Major. And since we do have, we have literally 20 people on right now, which is kind of crazy for this. Hi, everyone. Start the repo. It helps me out. It's free. Join the Discord if you want to get involved with all this cool stuff. And yeah, back to work on this. Move forward, move backwards first. From very mediocre movie. I guess it was a book first. Probably the book is better. I think I'll take a crack at Rubik's Cube. See in Raylib. Yeah, that'll work. I think that'll work. I don't know how complicated. Well, you don't need the solver at all, so it's probably a very quick little thing to do. Be a good, like, that's a good intro RL project. Like that would qualify for like this here, like section 5 of this. Heck, let's just tweet this right now that like all right, we're a little over 400 away from that. Cool. Let me add a couple quick sentences to this, and then we'll move on to the next thing for today. I believe I have another 40 minutes to do. Yeah, this paragraph I should spend more time on, I think. Just a little bit more time on this. Can read it today. I doubt it'll hit 10K today. I kind of hope it doesn't just do that instantly because I still have to get images. Like you need images for the articles at the top. But I guess I'll just do it today if I have to. Cause I promise I do it. Do star the repo though. Star the puffer. It helps us out. All right, we workshop this first paragraph so that like I'll add the thing actually. Jason, that advice was very good. And then the plan is if I have a little bit of time after that, we're going to start on the camera ready for my publication. I'm pretty sure that doesn't violate anything because it's already accepted. But yeah, we have where is it? Yeah, so this paper was accepted to RLC. So yay, there's finally going to be a Puffer publication. It's super outdated already because Puffer moves way faster than the conference cycle. But I don't know, I'll still show it off and we can edit a little bit today. I figured I'd do it on stream, because why the hell not? Not tomorrow, though. Tomorrow I'm traveling all day, and then I will be back streaming Thursday, Friday. Hello, Kyoko. Congrats on what? I guess there are many cool things lately. I didn't just instantly hit 10K, right? Like, that'd be kind of funny. No. Reinforcement learning is hard, and most of the material out there for beginners makes it even harder. It's the underexplored niche of AI that focuses on learning from interaction, and one of the few areas where you can really advance the field without a ton of compute. The advice here is a formalized robotics, fusion. People did fusion with it, right? Do logistics first. I haven't vetted the fusion one, which is a little sticky. Logistics, fusion, cooling, driving, design. Gaming. maybe super dumb question, but why is TD such a popular choice in RL? So it's not exactly, but the thing is that like everything's kind of TD if you squint at it, right? Like there's always like pretty much anything that you get, there's like some form of TD in it, and it's you need some sort of credit assignment is the problem, right? So like you get a reward later, and you need to figure out how much to care about said reward, and there's not a good way of doing that in general. So usually there's some sort of like fancy learned exponential discounting, which you write out as like a TD over n, right? It's mostly just like, what if you do regression? How? How would you do regression? What are you regressing? Like goal conditioned behavioral cloning. Well, that's no longer RL, right? Behavioral cloning, you're no longer learning from simulation data, you're learning from expert data. You need expert data to do that, and you can't scale it infinitely because you only have so much expert data. EBC. I do not consider, so it depends on your definitions. If you consider offline reinforcement learning to be reinforcement learning, then sure. I do not consider offline reinforcement learning to be reinforcement learning. It's a clever term that somebody came up for supervised learning in order to like sell it at a conference or whatever. The key defining aspect of reinforcement learning for me is interaction. So if you're not actually interacting with a sim or the real world or something, it's not RL. Defining RL as the specific class of algorithms makes way less sense than defining it as defining it through interaction. With a dash. No, it's literally, it's the right word. Shut up. Spell check. Applications include robotics, logistics, gaming, and even scientific simulation. It's calibration. Right? It was calibration for fusion. Control the plasmas, yeah. Well, it's control, I guess. I'll call it a control problem. Sorry if I jumped the gun. Reinforcement learning is currently an underexplored new. All right, we'll spend a little bit of time on this then to like make sure that this is good. Because this is ultimately the thing that is the most important. Also, did I do the same thing for my other one? It was like, there's the other article. Yeah, this is fine, because this is a personal article. Like, you read this because you already follow me. Or you don't read this because like you're not gonna read my advice on a topic that's like super subjective, if you don't already follow this. Like in RL, it makes more sense because it's more it's more specialized. But that's basically because people asked me for it. Okay. What I can't wrap my head around, RL, is why Markovian YTD it becomes. Because it's underexplored. No, okay, Sean, let me explain this. My guide explains this, okay? Ignore all the formalism about MDPs. TD is kind of okay, but it's like, whatever. Just ignore all the formalism about MDPs, though, alright? Ignore all of it. It's because that was the model that they could fit to the problems. RL is going to be a lot easier if you just view it as an empirical science, alright? Because none of the theory actually works, and like they'll basically RL is the field compared to other areas of AI where they'll write pages and pages and pages and pages of math, and none of it works. All right, and then the super simple thing without any theoretical justification or like any formal proof that works perfectly. So if you view it as an empirical science, like you will no longer be up at night over this. RL equals LMs. Actually, I think that there's probably better theory for general learning than there is for RL. So it's a weird combination where basically people in RL they try to write down more formal math than other areas of AI, even though they actually have less formal math that actually works. All right. And it's probably because MDPs exist independently, so it looks like, oh yeah, we can just model this as that, and we get all this really nice math. But then the thing is, none of it actually works. So what's the point? Like, a mathematical model is useful to the extent that it can actually predict the thing you care about, and if it can't, then it's not a useful model. And when you have a field where you can do work, but you don't have a mathematical model, that's an empirical field. Damn. I mean, it's not like the thing is, as soon as you give up that old perspective, right? As soon as you come and like look at this the way that we're doing it in Pufferlib, everything will make a lot more sense, and like you'll actually see the path to progress. I promise you. Because I pretty much in my head here, like if I just ignore everything else and I were to work on this stuff for like a year or two, I pretty much have the A to B to B, C to D to like RL solved. MDP is considered harmful. Are you serious? I was considering doing that. But I was like, you know what? I kind of piss off the academics as enough as is. Oh, he didn't actually write MDP is considered harmful. Oh, I see. He actually kind of did. That's cool. Who's this dude? Oh, Alberta. Okay. Yeah, so I don't... I guess you can put that stuff on archive, technically, but, like, academics love to do this thing where they kind of, like, fence each other with, It's like British Parliament, right? They, like, fence each other with, like, very couched language that's basically saying X thing is old and dumb, whereas I won't do that, and I'll just say, hey, this thing is old and dumb. Poker AI. Alright, cool. I've actually wanted to do poker and Pufferlib just to see. But we're actually, I think chess is probably the better one at the moment. We got lots of projects. I will retweet that with MDPs considered harmful. Funny. Also, continual learning as a category, like, continual learning doesn't need to exist. That's the other funny thing. There's not really a big difference at all with stuff. Reinforcement learning is the branch of AI that focuses on learning through interaction. Reinforcement learning is the branch of AI Reinforcement learning is about learning through interaction. Applications include robotics, underexplored niche of AI where you can really advance the field without a ton of compute. But learning RL and most of the material out there for big is hard. All right, like this was good advice from Jason. Reinforcement learning is about learning through interaction. Applications include robotics, logistics, gaming, and even control problems. I was at a loss for words for a minute to realize that RL is all empirical and the gap between theory and practical is huge. That was painful just listening to. Yeah, but the thing is, again, like, look at what we've built and tell me if it's painful. Okay? Did I show you this? Did I show you the Pong demo? Watch this. So we can kind of just show some people the stuff we build around here. All right. Puffer, train, puffer. Or let's do eval first. Puffer, Pong, just so you can see the difference. All right. Here's Pong. This is a random agent. It can't play at all. It barely ever hits the puffer back. We use a puffer for the ball because of course we do. Puffer, train, puffer, Pong. All right. This is something that usually, like, when we use Pong for research during my PhD, you'd have to overnight this because this would take hours. Okay, we're done. Here's your perfect Pong model, or almost perfect Pong model. It misses once in a blue moon. It never loses, though. And, like, that's the only demo that we have that's literally 5 seconds. But, in fact, we've even done it in 3 seconds before. But a lot of the environments train in, like, 30 seconds. And most of the ones that don't train in a few minutes. And then we have, like, a couple way harder tasks that are 10 minutes or 15 minutes. And then maybe a couple of tasks that actually take substantially more. Send you the challenge link? Thank you. We will be in touch over that. That sounds like a cool application area. Yeah, Sean, so one of the things as well that reinforcement learning just got stuck on for some reason is, like, academics, for whatever reason, they felt like the only thing that matters is that you can learn with less experience. That's the only thing that matters. All right, so if you have method A that learns Pong in 2 million steps, and method B that learns in 1 million steps, method B is way better. Even if method B takes 1,000 times longer in, like, compute. So basically what happened is, over the years, people did a ton of theory work, and then they trained on these really stupidly simple tasks very, very slowly because all their code was crazy slow and their algorithms were crazy slow. All right? And we kind of came along and said, okay, that's dumb. Let's just do everything with fast sims and try to make things run faster in wall clock time. And we'll just build fast sims. And lo and behold, in industry, if you can build a fast simulator, nobody ever says, well, can it train in fewer steps? Nobody cares. It's an entirely academic invented problem. All right? Now, yeah, there are cases where you can't build fast sims, and it's useful there. But, like, basically nobody even bothered trying to say, hey, wait a second, reinforcement learning can solve all these problems where we just build fast sims. Like, they didn't even do that. So, that's what we do. We'll get to sample efficient learning. It's not going to be that hard. It'll be fine. Like, with all the stuff we've built, it's not going to be that hard. We'll have to do some research, but it won't be that bad. Nowhere near as bad as it is now. Go through this paragraph one more time. Reinforcement learning is about learning through interaction. Applications include robotics, logistics, gaming, and even control problems in science like nuclear fusion. An underexplored niche of AI where you can really advance the field without a ton of compute, but learning RL is hard, and most of the material out there for beginners makes it even harder. Advice here is a formalized version of how I train new Pufferlib contributors. Some of these came in with zero programming knowledge and now help advance our research tools. The key is to start doing reinforcement learning immediately while filling in knowledge gaps slowly and in order of relevance. Through other words, reinforcement learning. In other words, reinforcement learning. That's fun. All right, cool. I like that a lot. I think this is set. Oh. Yeah, okay. This is doing very well. believe this Meta's MRQ style dynamics based learning integration into model free on model policy method. Go. Mr. Q, yeah. I gotta look at Mr. Q as well, for sure. I haven't like seen enough to put it into the post on it. Unfollowing. Okay, bro. All right. I will be right back. I'm gonna use the restroom. We'll spend a few minutes on the new paper. Then I gotta run for a meeting. I'll be right back though. All right. Cool. Let's take a quick look at the paper. On open review. I thought for a second that I was like wrong and it had been accepted. Yeah, there it is. There's the formal accept. I actually hadn't even seen that it was posted. So that would have been kind of awkward if I'd like gotten my tickets and everything. But all right. Oops. Yeah, meeting in 10. Let's see what I promised I will do. I do with this to make this get accepted, and we'll have to do that. Yeah, so this is all true. Submission articulates a tour de force, but it largely elects not to provide direct evidence. This is true. Okay, so it's granularity of reporting. The reason I didn't do this, by the way, and it's not a great reason, it's just because, like, it's always outdated instantly anyways. So, like, the best benchmark numbers are going to be you write the 10-line timing script, and you time whatever environment you want, and you yell at me if it's, like, gotten slower somehow. Missing, so unclear results. Pufferlib are easy. It's not easy to implement. Simple to implement. It's not easy to implement. Definition of throughput is missing. Emulation impact not negligible for environments faster than a few thousand. Gotten this to be better. Okay, so basically the complaints are like, hey, where's the evidence for all the stuff you claimed? Which is like the most relevant of possible claims, right? Except for the fact that I wasn't able to do this in the actual publication because there is a double-blind requirement. So I'm not allowed to link to anything. But like Pufferlib is literally the most transparent and visible RL project out there, other than maybe CleanRL, since it's like simpler. So it's like the evidence is kind of based on the fact that you can just go get it. But since I wasn't able to link to it, that was the main issue. Let's see what we have. Yeah. So basically it's this note right here. So contributions, let's see how dated this is. One-line wrappers that make complex environments like NetHack, NeuralM, MoGridley, etc. compatible with any RL library, support standard Gymnasium and Petting Zoo format. Context, Gymnasium, Petting Zoo are the most widely used environment formats. Pufferlib is compatible with the vast majority of environments using only a one-line wrapper. Drop-in vectorization for simulating environments in parallel. Most environments will see at least a 30% speed boost and 50% to 3x with pooling. The broadly compatible contribution applicable to nearly all environments. Context Gymnasium provides the most vectorization backend. It's slow for the reasons outlined in this paper. Puffer Ocean, a suite of 12 environments written in C that each simulate at over 1 million steps per second on a single CPU core. Context, a few of these have built-in AI opponents that can slow performance when search depth is increased. Base speed is greater than 1 million steps per second on a high-end desktop core. Some environments run at 10 billion a second. 4, a PPO demo that trains Ocean environments at 300K to 1.2 million on a single RTX 4090. Standard architectures are an MLP, LSTM, CNN and LSTM, 150K to 1 million parameters. Compatible with all third-party environments. Training is up to 30K steps per second on Atari. Still 30 times faster than the original CleanRL. So I think what we'll do, I cannot revise this to be a Pufferlib 3.0 paper. because it's basically a full rewrite. Pufferlib has changed so incredibly much since 2.0 that it's like you can't submit one paper and then revise it to be a completely different paper. I think even if it's strictly better, plus that's just a lot of work to do anyways. So I think what we'll do is we will add, if I have an extra page. Do I have an extra page? Well, I will go check the conference requirements after because I got to go in a minute here. But I'll check the page. What we'll just do is we will proof this. We'll just proof this to make sure I'm still happy with the paper as it's presented, to make sure that there's nothing like inconsistent. And then I will add like a short section, like a paragraph or whatever on like Pufferlib moves faster than the conference cycle. At time of writing, this is actually Pufferlib 3.0, which has 25 environments, is even faster and includes core algorithmic contributions that make it learn better than in Puffer 2.0 with base PPO. I think that's what we'll do. So we just add one paragraph. I think that's completely defensible. And then we have the paper as it is for 2.0. It's a little unfortunate because I probably won't ever publish like a 3.0 paper or whatever, but the thing is, by the time I would publish a 3.0 paper, we'll have Puffer 4.0. So I'm kind of fine with that. All right. Mr. Q looks a lot like Muesli. I'll go check this real quick. This is like a garbage website thing. What are the results on this? Okay, this is interesting, I guess. Reasonable param count. Interesting. Yeah, I gotta read this for sure. Did they say the wall clock time? Did they disclose their training time? Yeah, okay. Well, I'll come back to this. So for folks watching, thank you for tuning in. I will be back after a couple of meetings, most likely, because I got to finish this paper today, so. If you want to help me out for free, start the repo. It's free, really helps. You can join the Discord to get involved. And if you like what you see, follow me on X. That article will go live at 10K followers. Thank you.